Welcome, everyone. Today, we are going on a journey to the very edge of space, time, and, well, our own understanding. We're tackling one of the most powerful and mysterious objects in the entire universe, so get ready, because we're diving deep into the abyss.
So, let's start with a really simple thought experiment. Just imagine for a second a prison so perfect, so inescapable, that even the fastest thing in the entire universe, light itself, can't break out. This isn't some sci-fi movie plot. This is the fundamental reality of a black hole, and it's exactly where our story begins.
Okay, so to really wrap our heads around this, we need to understand what makes this cosmic prison actually work. Let's call this section the ultimate escape room.
The absolute key to understanding a black hole is a term called escape velocity. See, it's not a physical hole, not really. It's all about speed. Everything with gravity, planets, stars, you name it, has an escape velocity. It's just the specific speed you need to hit to break free from its gravitational pull. Think about it like this. To launch a rocket off our own planet, to get it away from Earth's gravity, you have to be going at about 11.2 kilometers per second. That's our planet's escape velocity. It's incredibly fast, for sure, but we can do it.
And then you have the universe's ultimate speed limit, the speed of light. As far as we know, absolutely nothing can travel faster than 300,000 kilometers every single second. This is the cosmic constant. It's the fastest anything can possibly go, period.
And this is where it all clicks. A black hole is what you get when an object becomes so incredibly dense, when so much mass gets packed into such a tiny space that its escape velocity, that first number, becomes bigger than the speed of light. And since nothing can go faster than light, well, nothing can escape. It's that simple. If you could somehow crush the entire Earth down to the size of a sugar cube, its escape velocity would be greater than the speed of light. And poof, you'd have a black hole. Okay, so if black holes literally trap all light, which makes them perfectly black against the, blackness of space, how on earth do we know they're even there? And that brings us to our next big question: how to photograph a ghost?
I mean, it's a real head-scratcher for astronomers, isn't it? The main tool you have for looking at the universe is light, but the thing you're trying to look at is a light eater. So how do you solve a problem like that? Well, scientists got really clever.
They came up with two main ways to do it. The first one is indirect. You can't see the black hole itself, but you can see the absolute chaos it creates all around it. Imagine a star getting ripped to shreds, or gas heating up to millions of degrees as it swirls down the drain. That chaos shoots out tons of powerful radiation, like X-rays, that our telescopes can pick up. The second method is direct, and it's a total modern marvel. You actually look for the black hole's silhouette, its shadow, against the super bright backdrop of glowing gas that's right behind it.
And believe me, this has been a long time coming. Way back in the 70s, a satellite called Uhuru saw these intense X-rays coming from a system called Cygnus X1, and that was our first really solid suspect. But the absolute game changer came in 2019. A planet-sized network of telescopes called the Event Horizon Telescope did what everyone thought was impossible. It took an actual picture of the shadow of a supermassive black hole. And then, just to prove it wasn't a fluke, they did it again in 2022, this time imaging the one right in our own cosmic backyard.
So let's meet the two celebrities. The first one we imaged, M87 Star, is an absolute monster. It's 6.5 billion times the mass of our Sun, sitting about 55 million light-years away. Then you've got Sagittarius A Star, which is the black hole at the center of our Milky Way. It's kind of small in comparison, at only 4 million solar masses, but it's way closer to home, just 26,000 light-years away. Seeing these two proved once and for all that these cosmic behemoths are very real.
So where do these things even come from? And what would actually happen if you got too close? Well, that brings us to our next section: birth, death, and spaghetti.
The most common kind, what we call a stellar black hole, is born from the death of a truly massive star. I'm talking more than 20 times the mass of our own Sun. After millions of years of burning bright, it runs out of fuel. Gravity finally wins the lifelong battle, and the core just collapses. This collapse triggers an outward explosion that is one of the most violent events in the entire universe, a supernova. It can actually outshine its entire galaxy for a little while. And if that crushed core that's left behind is still more than 3 times the mass of our Sun, nothing in the universe can stop it from collapsing forever. It just keeps getting smaller and denser, and that's how you get a black hole.
So what's with this spaghetti? Well, if you were unlucky enough to fall into a black hole, you'd experience something called spaghettification.
And yes, it's pretty much what it sounds like. The gravity pulling on your feet would be so much stronger than the gravity pulling on your head that the difference would stretch you out, pulling you apart vertically while squishing you horizontally, just like a piece of spaghetti. It sounds bizarre, I know, but it's a very real consequence of that kind of extreme gravity.
But here's the really weird part. When this happens actually depends on how big the black hole is. For a smaller, stellar mass one, the forces are so extreme that you'd be turned into spaghetti before you even cross the point of no return. But for a supermassive one, the gravity change is actually more gentle, so you could float right across the event horizon totally fine, only to get spaghettified much, much later, deep inside. Crazy, right?
So you'd think something born from all that complexity and violence would be incredibly complicated itself, right? Well, you'd be wrong. What they become is, well, shockingly simple. Welcome to the universe's simplest monsters.
So here's the thing. A star has all this stuff. It has a chemical composition, magnetic fields, maybe even things like mountains or valleys on its surface. But when it collapses into a black hole, all of that information seems to just vanish. According to something called the no-hair theorem, from the outside you can only measure 3 things about a black hole: its mass, how fast it's spinning, and its electrical charge. That's it. Everything else about that original star is just gone.
And that's exactly why it has such a weird name. The physicist John Wheeler joked that a black hole has no hair, meaning it has no extra complicated features sticking out. It's an idea that is both beautifully simple and profoundly strange. All that complexity is just shaved clean away.
All right, for our final section, we are going to bust a huge misconception and then talk about a discovery that completely changed everything we thought we knew. Let's talk about myths and evaporation.
Okay, here it is, the classic thought experiment. We all have this image of black holes as these cosmic vacuum cleaners, just sucking up everything in the neighborhood. So what do you think? If our sun just instantly turned into a black hole with the exact same mass, would Earth be doomed? Would we get sucked in?
The answer, which surprises a lot of people, is no, not at all. Earth's orbit would stay completely, totally unchanged. We would just keep circling that tiny point of darkness exactly like we circle the sun today.
And the reason is actually pretty simple. Gravity only cares about 2 things: mass and distance. Since the black hole's mass is the same as the sun's, and our distance from it hasn't changed, the gravitational pull is identical. Black holes aren't vacuum cleaners. You have to get incredibly close to be in any danger. Now, of course, without the sun's light and heat, the Earth would freeze over, so it would still be a very, very bad day for us, but we would not get sucked in.
But maybe the most shocking idea of all came from the legendary Stephen Hawking. He figured out that, because of some really weird quantum effects right at the edge of the event horizon, black holes aren't perfectly black after all. They actually leak a tiny, tiny amount of energy, which we now call Hawking radiation. This means they are very, very slowly losing mass. And over unimaginable amounts of time, trillions upon trillions of years, they will eventually just evaporate and disappear completely.
And this, right here, leaves us with one of the biggest, deepest, most unanswered questions in all of physics. If the no-hair theorem is right, and a black hole destroys all the complex information about whatever falls into it, but Hawking's idea is also right, and the black hole eventually disappears, then where does all that information go? Does it just vanish from the universe forever, breaking the laws of physics? This is called the information paradox. It's a profound mystery that scientists are still wrestling with today. And it just goes to show you that with black holes, the more we learn, the more we realize how much we have left to understand.
All right, welcome everyone to the Black Hole Comprehension Championship. This is it. This is where we find out if your cosmic knowledge is the real deal. You think you know black holes? Well, we're about to put that to the test. Let's see what you've got.
Okay, so the rules for this challenge, super simple. I've got 10 questions for you, and we're going to go through them one by one. No multiple choice here, you gotta know your stuff. I'll ask the question, you take a second to think, and then we'll reveal the answer. The goal, of course, is a perfect 10. You ready to go? Let's do this.
Let's kick things off with the most fundamental question of all. What is the one single physical trait that truly defines a black hole? What makes it a black hole? Think about its most basic core property.
And the answer is, its escape velocity is greater than the speed of light. Now, to put that into perspective, to escape Earth's gravity, a rocket needs to be going about 11 kilometers a second. But a black hole is so dense, its gravity is so powerful, that its escape velocity is more than 300,000 kilometers per second. That's the speed of light. Literally nothing in the universe is fast enough to get away.
Okay, on to question 2. This one is about a huge moment in science, a real game changer. What was the name of the massive international project that gave us our very first picture of a black hole back in 2019? That's right, it was the Event Horizon Telescope, or EHT, and this thing is incredible. It's not just one telescope, it's a whole network of them spread across the entire globe, all working together. They basically created a virtual telescope the size of planet Earth. That's how we finally got the resolution to see the shadow of a black hole. Absolutely historic stuff.
All right, question 3 is all about creation stories. These stellar mass black holes, they're born from the incredibly violent death of a giant star. What do we call that final, mind-blowing explosion?
You got it, a supernova. When a truly massive star, we're talking way, way bigger than our sun, finally burns through all its fuel, gravity wins. The core collapses in on itself, and that triggers the single most powerful explosion in the universe. If what's left of that core is still massive enough, nothing can stop it from collapsing forever into a brand new black hole.
Okay, time for a question about our own cosmic backyard. At the very heart of our Milky Way galaxy, there's a supermassive black hole that acts as the anchor for everything. It's our galaxy's big boss. What's its name?
That would be Sagittarius A star, or SAG-A star for short. It's the gravitational heart of our galaxy, hanging out about 26,000 light-years from us. And you know what's cool? In 2022, that same EHT team gave us our very own family portrait of this cosmic monster.
Okay, this next one is, well, it's a bit weird, and frankly, it's a pretty gruesome concept. If something falls towards a black hole, the intense gravity stretches it out in a very specific way. What is the wonderful descriptive name for this process?
And the answer, with probably the best name in all of astrophysics, is spaghettification. It's because the pull of gravity on the part of you closest to the black hole is so much stronger than the pull on the part farther away. That difference in force literally pulls you apart and stretches you into a long, thin string of atoms, just like spaghetti. A weirdly perfect name, right?
So you might think that black holes are infinitely complex, but this next question gets at their incredible simplicity. The no-hair theorem says that from the outside, a black hole can be described by just 3 and only 3 properties. What are they?
Those 3 magic properties are mass, angular momentum, which is just a fancy way of saying its spin, and its electric charge. That's it. The whole no-hair thing is a metaphor. It means all the other complex information from the star that died to create it, it's gone, wiped clean. All that's left are those 3 simple numbers.
This next one, man, this one really changed everything. It was a mind-bending idea from the great Stephen Hawking that connected Einstein's relativity with the bizarre world of quantum mechanics. What did he call the process where black holes can actually leak radiation and slowly evaporate?
And that would be Hawking radiation. It's a wild idea. Basically, at the quantum level, pairs of virtual particles are constantly popping in and out of existence everywhere. If this happens right on the edge of a black hole, one particle can fall in while its partner escapes. From the outside, it looks like the black hole just spat out a particle, and over billions and billions of years, this causes it to lose mass and shrink.
Time to bust a huge myth. This is a classic sci-fi question. Let's say, poof, our sun instantly becomes a black hole, but with the exact same mass it has now. What happens to the Earth? Do we get sucked in?
The answer is a big, resounding no. We would not get sucked in. It's a common mistake to think of black holes as cosmic vacuum cleaners, but gravity only cares about 2 things, mass and distance. Since the black hole's mass would be the same as the sun's, the gravitational pull on Earth would be exactly the same. We'd just keep orbiting it like normal, though it would get very, very cold and dark pretty fast.
For question 9, let's hop in the time machine. Since you can't see a black hole, how did we find the first strong evidence for one? The discovery of an object called Cygnus X1 was the key, and it was found because it was blasting out a specific kind of powerful energy. What was that energy? The answer is X-rays. But here's the clever part. The X-rays weren't coming from the black hole. They were coming from an accretion disk, a swirling, superheated platter of gas that was being stolen from a nearby star. As that gas got closer and closer to the black hole, it got squeezed and heated to millions of degrees, causing it to glow incredibly brightly in X-ray light. It was the ultimate cosmic crime scene.
All right, here we are. The final question. This is for all the marbles.
We talked about the project that took the picture, but what was the specific name of that very first black hole we ever photographed? That absolute giant, 6.5 billion times the mass of our sun.
And the history maker is M87 star. This absolute behemoth lives in the center of the M87 galaxy, about 55 million light-years from here. Seeing its picture for the first time, that was the moment an abstract idea in physics became a real, visible thing for all of us. A true landmark for humanity.
And just like that, we're done. 10 questions down. So the big question is, how did you do? It's time to tally up those scores and see what your official title is. Let's find out. All right, grab your notes, count them up. If you got a perfect 10, you are officially the Black Hole Comprehension King. Give yourself a round of applause. If you got 7 to 9, you're a black hole expert. Seriously impressive stuff. 4 to 6, you are a true cosmic explorer. And even if you got a few, you're a stargazing novice and you're just at the beginning of an awesome journey. Great job, everyone.
So whether you're a king or a novice, here's the most amazing part. For everything we've talked about today, we have barely scratched the surface. Black holes are still one of the biggest mysteries out there. They represent the edge of our knowledge, where our best theories start to break. And that means the greatest discoveries are still out there, waiting for us in the dark. The adventure is just getting started.